Precalc, this is 2.1, functions. So right off the bat, we're just going to start off with examples of functions, maybe what they kind of look like graph-wise. And then we have a little bit of a definition that will kind of change back to one of our original ways that we learned what a function was. And then talk about a few other things there before we move on to doing examples. So, first few things. An example of a function is your height as a function is a function of your age. So that means that as we age, we start to get taller to some point actually, and then I think it actually turns around and starts to shrink again, doesn't it? As we get older, our bones start to, I think they start to, like, the stuff between them, the cartilage and stuff, kind of shrinks, and you shrink down a little bit. So, so your graph or something like that might look, whoops, I'm going to start going up, plateau for a really long time, and then maybe start coming back down a little bit. Okay? So that would be a function, because it's something that's changing according to something else. Temperature is a function of the date. Obviously, we know in Wisconsin that our temperatures can range very greatly throughout even a day versus throughout the year. Some days we're at negative 20 degrees, and other days we're at 105. So it matters the time of the year, right? And so again, I think you would see the seasons go through where it starts really cold and it gets warm and then back down to cold again. And then again, kind of going back up. This one almost looks like more of a sine or a cosine curve if you look at the data probably throughout the whole entire year. Taking averages probably, right? I mean, there's statistical jumps in each one of those as well because each day itself could be slightly higher or lower. And then the cost of mailing a package is a function of its weight. The more it weighs, the more you pay. But now, think about this. Do they just automatically say that it's 3 cents an ounce or 3 cents for a half a pound or whatever it is? I don't know if anybody's ever gone to mail a package. Mailing's pretty much going out, right? For the most part. I guess package is not, but everything else. If you think about how things are weighed, obviously, right off the bat, it doesn't matter if it weighs minusculely, like a letter, it costs automatically a flat fee, right? We got the forever stamps. I don't even know what a forever stamp costs anymore. I just buy them because they don't tell you how much it is. But it automatically say costs the 60-some cents or 70, 80 cents, whatever it is. Up to a certain point, and at that point, you need 2 stamps, right? So it almost looks like one of these types of graphs. Does anybody know what those ones are called again? Step function. And usually it's got an open and a closed dot, right? Associated with it. So that means as it weighs a certain amount, the fee stays fixed. But as soon as you get to this point where it weighs, say, a pound, it jumps up to the next level. And then goes to 3 pounds. So you got variation. You have a range of weights that allow it to be a certain value. Of course, every one of us could look at those graphs and we should say, yes, according to the graph, every single one of those individually is a function. Why? What does it pass, guys? Yes, what? The vertical line test. It passes the vertical line test. Now, granted, I got them stacked on top of each other, so therefore it would not create a single function. But individually, remember, the vertical line test says that I can, or vertical, the true definition would be that if any vertical line can be drawn on a graph and intercepts more than once, it's not a function, right? We usually spin it the other way and say, well, if it only hits once or less, then it is a function. So you can look at it either way. Now, why is the step function still considered a function? Because I think we all are okay with this and this, but as soon as it gets to there or there, we start to have issues. Are at least in our minds, some of us have a little bit of issue. But why is that not an issue? Why is that not a problem? Okay.
Because when one's open, so
Yeah. One's open, one's closed. So one's included at that spot, the other one's not included. So therefore, there is no double stacking of your points. Therefore, it's a function. Everybody remember all of that? Not a big deal. So, going to the next part there is, what is the definition of a function? Well, our book says that a function f is a rule, okay? So it's basically a relationship that assigns to each element x in set A exactly one element called f of x, y, in set B. We've seen this probably slightly different, and I'll write it here on the bottom. The way that we have seen it is that there is exactly one output for every input, right? That's the way we learned it probably 2 years ago, 3 years ago. A function is exactly one output for every input, which is exactly what they're saying above that. It's just a little bit more wordy. We're talking about elements, which are elements are parts of sets. So you got a set that's going in, goes to exactly one output, which is exactly one output for every input. Now remember, it's A-OK if more than one input goes to the same output. Think back to your soda machine. They can have several buttons on there to go to Mountain Dew. Every single one of those buttons, though, better lead you to a Mountain Dew. If one of them all of a sudden leads you to a Mellow Yellow, we're a little upset, right? Because we all know that those are not the same type. You get upset. So it's okay to have multiple inputs to the same output, but an input better go to the same button or the same soda every single time. You don't want to just play this game of, I wonder what it's going to come out this time kind of game. Remember that when you see f with parentheses of x, it is read f of x or f at x, not fat x. Okay? So f at x, so that's how we are going to say. We're going to say it's a function made up of x's. Or we might take x out and put a 2 in there. So therefore, it's a function evaluated at 2. Okay? We're going to see some of that when we start to evaluate on the next slide. We also have the domain. We have the range. Domain are usually what? Or are the what? X are usually x when we're talking about functions. The domain is usually the y. X is the inputs, and our domain are the outputs. I also have there in parentheses independent variable and dependent variable. Independent, if you're independent, you have control. If you're dependent, there is no control. You just get whatever is coming to you, right? Kind of in a way. You kind of get what was already been decided to be put in. The rule already changes you. You get what it comes out. We also, I can think of this is, because the one way to remember that the range is your outputs. It's kind of like a driving range at golf or a hitting range for baseball or whatever. You control, you domain, you're independently choosing how you grip, how you swing, how you tilt your hands, all of those things. Those are all variables that are things that you're controlling on the way in. What you necessarily can't control is what happens after you've hit the ball, right? So at the range, it goes out, that's your output. It's dependent on what you put in, but you can't control that. Any questions? These are all review, right? Everything we've seen before. So, let's actually put it to use. I forgot to clean this one. Okay. So the first example they want to bring up is the squaring function that basically assigns each real value number x It's square of x squared. Definition, f of x equals x squared. We've seen this many, many, many times before. We know how to handle that. Basically, though, I want you to evaluate the function for f of 3, f of negative 2, and f of the square root of 5. So, how do I do this? Okay. We all know that if I'm going to substitute a value in, you should be using parentheses. So we're going to do f of 3 equals. Now I remember, or I think of this as transplanting flowers. If I'm going to transplant a flower, I need to remove the flower that's already there. The flower that's in this problem is an x. So what I'm going to do is I am officially going to tear the x out, leaving a hole that's going to be filled with the new flower, and the new flower is a 3. And then you just have to evaluate. Ask yourself, 3 squared is 9. You're just using basic substitution properties here. Now, to properly say this equation, now if it's all chained like this, it makes sense that f of 3, which is equal to 3 squared, was equal to 9. But some of your answers might have to be listed as saying what is the value at f of 3, or it might be a multiple choice, it might be used somewhere else, and so you may have to list it as the f, the function, evaluated at 3 is equal to 9. That's a proper way, using function notation, to listing this. Do not make a freshman Algebra 1 mistake by dividing both sides by 3, thinking, oh, we're in algebra, I need to get f by itself, I need to solve for f. No, you're not solving for f, you're solving for the function evaluated at 3. So therefore, the function evaluated at 3 is 9. Done. That's your answer. Do the same thing for f of negative 2. The function evaluated at negative 2 is, again, something squared, and that something is negative 2, which is what? 4. So f of negative 2 is equal to 4. Done. So I'm assuming most of this should not be a problem. It should be a relaxing time. And what happens when you square a square root? They cancel each other. The answer is 5. So f of square root of 5 is equal to 5. Not that big of an issue. Now, what is an issue sometimes is actually having to list the domain and range of the function. Now, this one they're asking domain and range. Why? Because you guys have seen this so many times. You guys should know what it looks like. And I think every one of us, when I said f of x equals x squared, we all have an image of what an x squared graph looks like. But most of us agree that it would look something really close to this. Because we've graphed it before, we've seen this, we've actually made t-charts for this thing many times. Well, then we took this, and then we moved it left, right, up, down, stretched it vertically, horizontally. We do all of those things. Flip it about the x-axis, y-axis, all of that. So, the question is, what is the domain? What are the x values that I can put in? What are the x values maybe I cannot put in? So what I say is put D with 2 dots, bracket, x, because x is our domain, such that, which is a straight line. What are the values of x? Is there any values that I can't be? It's all real numbers. It goes on this way. I can put any value I want over here, or I can put any value over on this side, which means I'll get a value out. So it's all real numbers. So I could write all real numbers. Good. A shortcut way, does anybody know? Anybody? Yeah, the E thing, right? So we would say such that x it looks like a C with a line, is in. Sometimes they make it R with an extra line on it. X is all real numbers. X is contained in the real numbers. Now, if there would have been some reason that it can't be a 2, then I would also possibly add in there that x cannot equal 2 with that equal sign, right, with the line through it, that x can't equal 2. Range. Looking at my graph, what do you think the range is? That's a y such that y is greater than and equal to 0. Why? Does the graph go below 0? Can't square a number and get it negative, can you? So therefore, the only y values that come out are 0 and bigger. So you have to use inequalities for these. Could we have used interval notation for this? Sure. Okay. Any questions on that? We're going to do a little bit more on the domain at the last slide. And then we step it up a little bit with evaluating our functions, and we ask you to evaluate a polynomial. This one's only a quadratic, but it could get bigger. So, evaluate for f of negative 2. The only difference between this problem and the problem above it is that there's 2 different places where x is. So I remove x twice, substitute in negative 2 twice. F of negative 2 is equal to 3 times something squared plus something minus 5. And the something is what? What's going in there? Negative 2. And from this, you just use your order of operations. Use PEMDAS, left to right. Good to go. Negative 2 squared. Notice I kept the parentheses still. Subtract a negative. Oh, subtract a positive. Or positive adding a negative would just be subtract the positive. Cleaning this up some more. 3 times 4 minus 7. Which equals 5. So to finish it up completely, we would state what? Nothing too bad. I'll give you guys a couple seconds to do the rest. Okay, as you guys are finishing up probably the last one. I think part B is probably the easiest one, right? F of 0 is 3 times 0 squared plus 0 minus 5. 0 makes things go to 0 quite often, so the answer is negative 5. It's generally an easy one. I'll skip over part C, because again, that's just substitute and a nicer number. But part D actually has you do a fraction. So if I want to substitute in a half, again, I'm using parentheses. I'm showing all of this. That's great. But then I'm going to start to evaluate. What's a half squared? It's a quarter or a fourth. I'm going to get rid of the parentheses on this one. Minus 5. At this point, I see that I'm going to have probably what in the beginning? 3 times a fourth is 3/4. A half minus 5. I need to have a what? Common denominator. Common denominator of what? So 3/4, good to go. Half becomes what? 2/4. And a 5. Oops, that's a minus, right? Negative 20 over 5? 4, sorry. 5, 4. And now 3 plus 2 is 5 minus 20. Negative 15/4. So f of 1/2 is equal to the function evaluated at 1/2 is negative 15/4. And then, of course, we kick it up another time, and we introduce this thing again. What are these called? This has got a special name. Really? You guys know this. Piece it together, guys. Piecewise! Hey! It's a piecewise function. It's a function made up of pieces of other functions. So, remember, the whole idea of this, though, hinges on the fact that it creates a function still because of this, your domain checker. Now, granted, guys, we're not graphing these right now. We're just evaluating. So you can see that the top one's a line, the bottom one's a quadratic, and they seem to do something right around 1. Can you guys see that? So, just for fun, let's make a quick sketch of that. We know that there's something happening about 1, because that's where one graph stops and the other one starts. If I graph the first equation, we know 1 is an intercept, and it has a slope of negative 1. So really, it goes this way. Is this graph included at 1 or not? Are we included? Yes, the domain says it is there. The other one's that quadratic, the squaring function, which means 0, 0, 1, 1, stuff like that, right? So it's going to look like this, not included, and go up. I don't know if I like that. Something like that. Can you guys agree with this, that would be kind of a rough sketch of what this graph would be, without actually naming too many points? So you can look at that. Is that a function, first of all? Yeah. Made up of others. Remember, the whole idea here is I need to evaluate for these values here. But to do that, I just need to say, hey, where is negative 2? Well, negative 2 is on the left side, and negative 2 would be on this part of the graph. This part of the graph is the line, which is on the top. Well, that's great if I had a graph, but originally I didn't have a graph. So all I have to do is check it against the domain. Is negative 2, or where does negative 2 make it true? Is negative 2 less than or equal to negative 1? Yes, that's true. Is negative 2 greater than 1? No. So it doesn't make the bottom one true, so I'm not going to plug it in there. I will plug it into this top one, which means g of negative 2 is equal to 1 minus negative 2. And when you subtract a negative 2, you adding, which equals 3. G of negative 2 equals 3. So it's really not that bad. If I put 2 and 3 in, 2 and 3 satisfy the bottom, so then I just square them. Easy enough. I think sometimes the hardest point to decide is the one at the domain change. It happens to be a 1. Which one of these equations does 1 go into? Top or bottom? Top, because it's equal to. So in that case, g of 1 is equal to 1 minus 1, which equals 0. In our graph, that obviously you can see that. So g of 1 equals 0. Okay? I'm skipping the other 2 because it's the same thing. You just have to use the bottom equation because it makes 2 is bigger than 1, 3 is bigger than 1. You're good to go. And then we kick it up even more. We kick it up another notch here with the fact that we are going to evaluate with a variable, with a negative variable, with another expression, and then we're going to put a whole bunch of things together for part D. And I'll tell you guys, part D is actually the start of taking derivatives, which is calculus. You will spend the first month or so doing stuff like D with a limit on it. And when you do that, you get very frustrated because it ends up becoming very heavy in algebra. And we forget a lot of our skills in algebra. And then, a month into it, your teacher goes and says, oh guys, this is called a derivative, and all you have to do is this. And within 3 seconds, you're like, I can do the whole entire problem in 3 seconds versus 25 minutes. And they're like, yeah. And everybody gets kind of upset at them. But that's the way it goes. You got to learn the way to do things the hard way, the long way first, and then they'll show you the little shortcuts. So, evaluating for A is what happens if I take the function and I want to write it in terms of A. Not that big of a deal. You guys are like, oh, I just got to sub in an A for X. Notice what I'm still doing, guys. Did I really need the parentheses? No, because it's a positive variable. It's fine. I still do that just to keep myself in check. And then I can clean it up. And now I've just created a function only in A's instead of X's. Because in part B, do you need the parentheses? And the answer is yeah, you do. So be very careful. But again, is it really any different than what we just have been doing? No. Just make sure that you use your order of operations correctly. Because when you square a negative, it still becomes positive. When you multiply positive and negative, though, it becomes negative. And so now f of negative a is 2a squared minus 3a minus 1. Hey, guys. By knowing that information in part B, is this function symmetric about what axis would that actually be testing for? The y-axis. Is it? Was I able to put in a negative? If I change it to x, it would be the same thing with just x's. Is this equation the same as our original equation, or this one? No. So therefore, it's not symmetric about the y-axis. Interesting how we can put all that together. I think part C is probably one of the hardest ones that you guys will probably have to encounter. Because I got an expression, another function, that I'm putting into a function. So f of a plus h equals to a plus h squared plus 3 times a plus h minus 1. And what happens is a lot of students forget binomial expansion. Again, they're going to put a squared plus h squared and call it a day. We need to get past that, guys. Too much of that on the quiz. We need to understand that you have to FOIL if you can't remember the pattern, but I think by now we should start to remember that pattern. This becomes 2 times a squared plus 2ah plus h squared, parentheses around that, plus 3a plus minus 1. Multiply the 2 in. 2a squared plus 4ah plus 2h squared plus 3a plus 3h minus 1. That is f of 8 plus h. Or can we simplify that? Can we gather anything up? Now, someone did ask earlier, well, shouldn't I move like the 3a closer to the 2a squared and those types? Sure. If you want to start grouping, to probably kind of group things into standard form in a way, that's an option. But that's it. And then notice that part D, you need to take what you found here, subtract f of a, and then divide it by h. So, to save time, I'm going to say it's that whole entire function on the bottom minus the whole entire function of f of a, which was what? 2a squared plus 3a minus 1. And I'm going to put all of that over h. If h never equals 0. Again, to save some time and space, I'm going to change the signs, right? Because I'm subtracting a group. That means there's a negative 2a squared. There's a negative 3a and plus 1. But when I do that, what happens on top? When I start to combine? I start canceling things out. The negative 2a squared cancels with the positive 2a squared. The 3a cancels with a negative 3a. And negative 1 cancels with 1. I have to move it up above. So what I'm left with is 4ah plus 2h squared plus 3h all over h. What can I do now? Take an h out. Get the h out of there. A plus 2h plus 3. Wait, did I mess up? That's a 4 in front. Let's say that doesn't look right. 4a plus 2h plus 3 all over h cancels. And that's what I'm left with, right? Here's the thing. Eventually, you would take the limit of this and say, what if h does go to 0? Then you're left with 4a plus 3, right? Guess what, guys? 4a plus 3 is the derivative of this equation. And how you take a quick derivative is you take the exponent, multiply it to the coefficient. 2 times 2?
4.
Subtract 1 from the exponent is 1. So that'd be 4x, right? Do the same thing here. 1 times 3? Subtract 1 will be 0. X to the 0 power is 1. And the derivative of a constant is 0, so it's not there. So you end up with 4x plus 3. And that's what we would have here. Granted, we're in A's instead of X's now. But you guys seeing that you're going to have to do something the long way for a long time before they start showing you the shortcuts. The last ones that I want to talk about are the ones that are just going to ask you to find the domain. So I gave you a little key here. We're just going to assume, without even having to say it, it's all real numbers. Except in places where it makes the denominator 0, or make the function not possible. So in our first problem, f of x equals 1 over x squared minus x. It's a fraction. What can't be true about fractions? You can't divide by 0. So therefore, I'm going to factor that denominator. And you get this, right? So what values of x can it not be? 0 and 1. So the domain is going to be all real numbers, x, such that x can't equal 1, x can't equal 0. Done. The line means such that. Kind of says, hey, I'm talking about x's where the rest of this has to be true. Part B. What's the biggest thing we're talking about there? What's the overarching theme? I got a function inside of a function. Can I square any number I want? Yeah, that's not an issue. What's the restrictor? The square root. What do we know about square roots? Can't be negative. So that means the number inside, the thing inside, has to be not less than or equal to, but greater than or equal to 0, right? So on this one, it'd be 9 minus x squared has to be greater than or equal to 0. Can you solve for x? 9 is greater than or equal to x squared. Square root. X is less than or equal to 3. If you want, you can change that as this, either or, right? Just change the order around. So, your domain x such that x is less than or equal to 3. Done. Anything else won't work. But if I put those in, I'm good to go. Part C, without having to write it down, we have a couple conditions. We got a fraction, and we have a square root. You just have to combine them. The square root says it can't be negative, yes? But then it also can't be 0 inside, because then it'll be a 0 on the outside, which makes it divide by 0. So instead of being greater than or equal to 0, it's just greater than. So where is t plus 1 greater than 0, and solve for t? So your domain, guys, your domain would be bigger than, or you're going to be talking about t, sorry. So then therefore, it's not x such that, it's t such that. Your homework is 13 through 15 and 29 through 32 on page 152. Have a great day.